Hi guys, we will be talking about normal probability distributions and their graphs in this video. We will graph normal curves and summarize the important properties of them, and we will apply the empirical rule to solve real-world problems. So to start off, a density curve describes the overall pattern of a distribution. So below are some examples of density curves. They are always graphed on or above the x-axis. The area inside each density curve will always be 1. The median of a density curve is the place that splits the curve into equal areas. So in this example over here, the area to the left of the median would be the same as the area to the right of the median. The mean of a density curve is called the balancing point. If this curve were made out of sheet metal and you were to balance it, the mean is the point where it would balance. And here are some images to display that balancing point. So in this last one, you can see that the curve balances at the mean. And remember, the mean, or the population mean, is denoted mu. On the previous slide, we looked at a few density curves, but a density curve that is symmetrical and bell-shaped is called a normal distribution. And here are a few important properties of the normal curve. A normal curve is smooth and symmetrical about the vertical line extending from the mean up to the curve. So that's a line of symmetry in a normal curve. The curve approaches the x-axis but never touches it. So on this end, it goes to the left forever, and it goes to the right forever, and it gets closer and closer to the x-axis, but it never actually reaches the x-axis, even though it kind of looks like it is really close. It just never reaches it. The parameters that control the shape of a normal curve are the mean and the standard deviation. So any curve with a unique mean and standard deviation would have a unique curve shape. The highest point of the curve occurs over the mean. If the distribution were graphed on a piece of sheet metal and cut out and placed on a knife edge, the balancing point would be at mu. We talked about that on the other slide. If I put a fulcrum right here, it would balance at that point. The standard deviation determines the extent of the spread. If the standard deviation is large, the curve will be more spread out, and if the standard deviation is small, the curve will be more peaked. And here are some examples of those shapes. This larger standard deviation gives us a more spread out curve, meaning the data values are further away from the mean, and a shorter or a smaller standard deviation gives us a more peaked shape because the data values are clustered closer together, closer to the mean. And as in any density curve, the area under the entire curve is 1. So this area under here, this area under here is always 1. And if you notice looking at the diagram above, we have the mean in the middle. We go up 1 standard deviation, we go up 2 standard deviations, and we go up 3 standard deviations. And we also go down 1 standard deviation, down 2, and down 3 standard deviations. Here's an example. Shown below are 4 normal distributions labeled A, B, C, and D. Use these curves to answer the questions that follow. What do curves B, C, and D have in common? Well, since they're all normal curves, they're all symmetrical about the mean. They are all bell curve shaped. And curves B, C, and D all have that same line of symmetry, and that is the mean, so they have the same mean. Which of the four curves has the smallest standard deviation? Well, the one that is most peaked and the least spread out is going to have the smallest standard deviation, and that would be B. Which of the four curves has the greatest standard deviation? That's going to be the curve that's the least peaked and the most spread out, and that would be D. Which of the curves has the lowest mean? Well, that's going to be curve A. Its mean is down here at -2. The other means are all 0. Now we're going to talk about the empirical rule. For a distribution that is symmetrical and bell-shaped, in particular for a normal distribution, approximately 68% of the data values will lie within one standard deviation of the mean. You can see down here, 68% is either one standard deviation above the mean or one standard deviation below the mean. 95% of the data values will lie within two standard deviations of the mean. Down here you can see that from 2 standard deviations below the mean to 2 standard deviations above the mean, 95% of the data values would fall in that space. And the last part, 99.7% or almost all of the data values will lie within 3 standard deviations of the mean. So within 3 standard deviations is almost all of the data values, 99.7%. Notice that the empirical rule is a stronger statement than Chebyshev's theorem in that it gives definite percentages, not just lower limits. The empirical rule applies only to normal or symmetrical bell-shaped distributions, whereas Chebyshev's theorem applies to all distributions. In case you forgot, here's Chebyshev's theorem. It stated that at least 75% of the data fell within 2 standard deviations of the mean. But with the empirical rule, if the data is normally distributed, 95% of the data is within 2 standard deviations of the mean. Chebyshev says 88.9% of the data falls within 3 standard deviations of the mean, but for normally distributed data, 99.7% falls within 3 standard deviations of the mean. So it's definitely a stronger statement and more specific, but only applies to normal distributions. In this example, we will use the empirical rule to solve a real-world problem. According to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. Sketch this distribution, labeling the mean and the points 1, 2, and 3 standard deviations from the mean. So we're going to put the mean in the middle, below that high peak, and the mean is 149. That's mu. And then the standard deviation is 9. So I'm going to go up 1 standard deviation by adding 9 to 149, which gives me 158. I add 9 again to get 2 standard deviations above the mean, and that's 167. And then I add 9 one more time and get 176. I'm also going to subtract 9 from the mean, and 1 standard deviation below the mean would be 140. Subtract 9 again, 131, and subtract 9 one more time, and I get 122. Now, if I divide this up, 68% of the data is going to be between 140 and 158, 1 standard deviation above or below. Dividing 68 in half, I get 34% in this part, 34% in that part. So remember, from here to here is 68% of the data, and we go up 1 standard deviation and down 1 standard deviation. Now, between 131 and 167, 95% of the data values will be within 2 standard deviations above or below the mean. If I subtract 95 minus 68 and divide it by 2, I get 13.5% in this part right here and 13.5% in this part right here. And 99.7% of the data values are going to be within 3 standard deviations of the mean, leaving us with 2.35% in that section and 2.35% in that section. Now we have a tiny little bit left, 0.3% left, so 0.15% will be above 3 standard deviations and 0.15% will be below 3 standard deviations. And that adds up to 100%, which is equal to 1 in decimal form because the area under this curve, remember, is always 1. About what percentage of 12-year-old boys will be over 158 centimeters tall? Well, if I add up this 13.5 part, the 2.35, and this little 0.15, I get 16%. So 16% of 12-year-old boys would be over 158 centimeters tall. About what percentage of 12-year-old boys will be between 131 and 140 centimeters tall? 131 and 140 would just be this little part right here. That's 13.5% of the data values. About what percentage of 12-year-old boys will be between 149 and 167 centimeters tall? 149 to 167 would be those two parts right there. 34% plus 13.5% gives us 47.5%. And about what percentage of 12-year-old boys will be at most 131 centimeters tall? That is this part to the left of 131. And so we are going to add up 0.15% plus 2.35%, which gives us 2.5%. This example is similar to the last one. I recommend you try it yourself and then just check your answers when you're done. The yearly wheat yield per acre on a particular farm is normally distributed with a mean of 35 bushels and standard deviation of 8 bushels. So I'm going to go up 8 and I get 43. I add 8 to that, I get 51. I add 8 to that, I get 59. I subtract 8 from the mean and get 27. Subtract 8 again, 19. Subtract 8 again, 11. And then we're going to divide the normal distribution into those percentages. It's always the same, 34 and 34 in these two middle chunks, and 13.5 and 13.5 in the next two chunks. And then we get 2.35% and 2.35%. And these teeny tiny parts at the very end are 0.15% and 0.15%. What is the probability that an acre will yield between 19 and 35 bushels? 19 to 35 would be this part. So we are going to add 13.5% plus 34%, which gives us 47.5%. In part B, what is the probability that an acre will yield 43 or more bushels? 43 or more would be from here all the way to the end. And So we're going to add 13.5 plus 2.35 plus 0.15, which gives us 16%. What is the probability that an acre will yield at most 43 bushels? At most is the same as less than or equal to 43 bushels. So less than or equal to 43 would be from 43 all the way to the left. And since it's so much of it, it might be easier to do 100 minus the part that I didn't shade. So I'm going to do that. 100 minus, I didn't shade the 13.5, the 2.35, and the 0.15. And so that gives me 84%. And the last one, what is the probability that an acre will yield less than 19 or more than 51 bushels per acre? Less than 19 is this end. More than 51 is that end. If I add those up, well, they're the same area, so I'm going to do 2 times 0.15 plus 2.35, which gives me 5%.